once you turn the flashlight off, if it was 1 light year away, it would hold it up. It would take 2 USBs to the first spot. But then after you moved it, you would see it move. Well, everything would be delayed 2 years, but you can see the spot move really quickly. All right, I'm going to go. So ask me later. All right. So 37. What does this put us at? 53. All right, here we go. Okay, welcome to spaceship relativity, which is actually more in the special relativity series. So there's special relativity 1, 2, and 3 behind you. Soon I'm going to get to quantum paradoxes, but we're in special relativity right now. So if you're in a spaceship, what do you see? We're actually going to do trains a little bit too. So what is this? Who am I? My name is Robert Nemeroff. I'm a professor of physics at Michigan Tech, and this is Physics X, also called Extraordinary Concepts in Physics. This is actually being taught for credit at Michigan Tech, and there are students right in front of me, real students. This course is being taught in 15-minute segments and does not require a textbook. Even if you're not in the course, even if you're just surfing around on the web, please feel free to click and enjoy and post comments. Okay, so now we're going to get into one of the more controversial paradoxes of special relativity, the Ehrenfest paradox. Einstein himself was considered thinking about this. He thought about many of them, actually. He was really good at these. Probably the best of anybody. So a rigid ring, you just have a ring, and you start to rotate it. What could be simpler than that? You got a ring. You rotate the ring. Simple, right? What's the problem? Does its radius decrease? So this is reformulated in a way that there's actually something that happens. You would think it might if there's Lorentz contraction, right? Fast things, they contract, right? Does this radius decrease? Okay. So reformulated, let's say you have train cars that sit on a circular track connected by taut strings. So here's your circular track, and you have train cars here, and they go all over the track, and they're equally spaced even though I can't draw, and they're connected by strings. So then these cars begin to circle the track. So it's like rotating the ring. It's the same thing. What happens to the strings? Do the strings droop? Do the strings break? Do the strings remain the same? Or did Ehrenfest, should we just ask Ehrenfest because he's the one who thought of this? This is a tough one, and people have debated this even in the literature for a while. This gets at the heart of some of special relativity in some ways because here you're not just seeing things. Here, if there's going to be contraction, a string is going to break. It's a little different. So is this contraction real enough? Is this special relativistic contraction real enough to break strings? Or is it just these visual anomalies that we see? And let's see. Oops. Sorry, I've got a little thing over here. Let's clear that and go to the next slide. The strings, it turns out, break. So there's something to this contraction. Length contraction actually makes the length of the train cars plus the strings contract. Every observer sees the radius as constant. However, observers rotating with the ring measure a larger circumference than observers at rest. Therefore, there's not enough, you need to stretch things. They're not connecting anymore. You need longer things because the person rotating with the cars sees the strings plus cars as occupying a longer length now. But the cars are too rigid to stretch, but the strings, they can break, so they break. So the cars plus the strings are now not long enough to cover the larger circumference. And this was a tough one, debated by many physicists for many years. And Einstein himself, I've actually tried to change the font on this, and it just won't let me do it. Google Docs don't let me do it. Einstein himself actually came to agree with this solution, that the strings break. And it's a fundamental experiment in special relativity. Hasn't actually been done, but it's agreed upon what would happen. Okay. Bell's spaceship inequality. Who's this Bell? Well, there's a famous Bell who is involved in quantum mechanics and Bell's inequality, and yes, he was interested in special relativity as well. And he asked the question, two spaceships connected by a string, they both accelerate. What happens to the string? Does that string break? Or does it not? Or does it become taut? So here's three things. String will droop. Since length contracts, string will cover less length and bunch up. The string will break. Since length contracts, the string between the ships contracts but still must cover the same distance. Therefore, it can't cover the distance and it will break, or it will just remain the same. Because if you're in the spaceship frame, then shouldn't everything just remain the same? Just like if you're in the frame of the Ehrenfest paradox of the rotating cars, the trains going around the track. But the trains going around the track actually are a little different because they're going to actually notice an acceleration. They're not an inertial frame, strictly. Or they're asymptotically in one as you go far out. But these spaceships are going in a straight line. Are they going to break their strings or not? So the answer is controversial. And it actually gets, sometimes paradoxes in special relativity don't have simple, clean solutions like the Ehrenfest paradox. This one depends on when simultaneity in which spaceship actually begins accelerating first and what the exact magnitude of the acceleration of each spaceship is. You can get them to accelerate such that the strings always remain taut and never droop and never break. However, due to some ways of making this up, and this has been debated in literature, they will break if you accelerate the spaceships in some way, and they will even droop if you accelerate the spaceships in other ways. Okay, so here's something a little bit different. Is it possible for a human to go anywhere in the visible universe in a human lifetime without violating the laws of physics? This is, again, something I thought about a lot when I was an undergraduate. Here we have time dilation, which means that if you watch somebody in somebody's frame, their clocks appear to run slow. Of course, if you're in that frame, you're running slow and your clocks are running slow, so when you look at your watch, you say, oh, it's running normal speed. However, when someone in a different moving frame looks at your watch with their telescope, they say, no, that watch is running slow. Can you use this to go anywhere in the universe you want? No, because in order to do that, you must travel faster than c. Yes, you can do that because time dilation will save you. So the universe, again, starts to run slow, starts to contract, and if it runs slow and contracts, then I can get anywhere I want because it will be a universe that's contracted, so I can just go anywhere. And have I watched too much Star Trek so that I now begin to believe warp drive is real? Which of these is the solution? And the answer is you can go anywhere you want in the universe. So if something is 10 light years away, or let's say something is 100 light years away, and you think, well, I'm not going to live 100 years, I can't go there. The galactic center is 100,000 or so light years away. I can't go there. I'm not going to live 100,000 years. Not true. You can go. You just have to go really fast. And if you go really fast, length will contract and you can get anywhere. The problem is not one of physics. The problem is one of engineering. We can't create a spaceship that can accelerate like that. So you might think, okay, I can go there, but the speeds will kill me. But you can't tell you're moving at any speed. In fact, you can accelerate at 1g, which we're all experiencing right now. One acceleration toward the Earth, one Earth gravity toward the Earth. You can go anywhere at 1g, and at one acceleration you can go anywhere in the universe in a normal human lifespan. This is essentially like the twin paradox in a way, with you being the twin that leaves, except there are differences because even though you're accelerating at 1g, you could do this by going at a constant speed, and therefore each twin could do this. So there are differences. The universe contracts, as I said. This website here is one that will tell you some details of how to compute these things. So you can go to the nearest star. The nearest star is about 4.3 light years. And if you were traveling at 1g, one Earth acceleration in a spaceship, if you could sustain that, you could get there in 3.6 years. You could go there. Vega, a bright star, one of the brighter stars in the sky, is 27 light years away. At 1g, you can get there in 6.6 years. Center of the galaxy, 30,000 light years. Now we're clearly above human lifespan. 20 years to get there at 1g. The nearest major galaxy, M31, the Andromeda galaxy, 2 million light years away. You can get there in 28 years. The problem is if you come back and you want to tell your friends, sorry I was away for 28 years or 54 years, 56 years, no, they'll be long gone. By the twin paradox, it prohibits you from coming back and telling your family and friends what you saw, but you can do it. You can go out to a redshift of 1, which is 11 billion light years away, co-moving radial distance if you're quantifying distances in cosmology by different means. 45 years you can do it. So you can stay alive for 45 years. You can go out to the distant universe. You can go as far as we can see the microwave background, which I talked about last lecture, where photons broke free from electrons and the plasma universe and came to us, and creating something that's 45, essentially co-moving radio, 45 billion light years away. You can do it in only 48 years. The general formula is 1.94 times the hyperbolic arc cosine of n, which is light years, divided by 1.94 plus 1. So how come this 1.94 is this strange number? Well, that's because g, the acceleration we're used to, is a strange number. So it's related to that. Okay, so I got to clear the blue. And I like to use this as a warp, the equivalent of warp speed. People say you can't have a warp drive. I say you can have a warp drive, you just can't come back. You can go at what would be warp whatever it is. Warp 1 would be the time needed, would be the speed a spacecraft must take to travel 1 light year as measured in the Earth's frame by 1 light year's time on the space starship frame. So if it's 1 light year away, you could go at warp 1 such that it takes you 1 year's ship time to get there. That's a way of interpreting warp. If you went at warp 2, well, I guess it wouldn't take you 2 light years to get there, but you can make something so equivalent. So here's one. How fast must one travel to go 10 light years away while experiencing only 1 year's worth of time passing? Okay, here's a way of quantifying it. That would be warp 10. You go 10 light years in 1 year of ship passing time. You can call that warp 10. So Star Trek sort of works, but you just can't come back, or the twin paradox will have you travel into the future. So can you use the twin paradox to travel into the past? As I mentioned several slides ago, the answer, obviously last lecture, the answer is no. You can't travel into the past. You can't see the battle of whatever it is you wanted to see. You can't travel into the past, but you can travel, if you go fast enough, you can go effective warp speeds. You can see anywhere you want in the universe, but you can't come back and talk to anybody you knew about it. So that will wrap up this lecture. It's a little bit shorter than the average one, and next time we'll be doing some quantum mechanical stuff, 2 slit experiments, but until then, please remember to keep Schrodinger away from your cat. Thank you.